So today we're going to look at Chapter 7 and hypothesis testing. So an introduction to the null and alternative hypotheses. So in this first example here in our starter, we're told we've got a random variable x which can be modelled on a binomial distribution where n is 20 and the probability of success is 0.4. Calculate the following. So if we want to calculate the probability that x equals 5, what we do using our calculator, our classwiz calculator, press the menu button 7, then press 2 for variable, and we want to use the binomial PD because we just want the probability it equals 5, not less than or greater than. So equals 5 is a PD. So our x value will be 5. Our n is 20. Because remember, binomial distribution, our parameters are n and p, where n is the number of trials and p is the probability of success. So in your calculator we've put n equals 20 and our p here in this case is 0.4. And when you put that in, you'll get your probability. So you should have found that p equals 0.75. To answer B, the probability x equals 10, again, we're going to use a binomial PD and input the values into your calculator. So menu button 7, variable, and then binomial PD. And your x you're going to say is 10, your n, there are 20 trials, and our p you'll put in as 0.4. And when you put that in, you'll get the probability. When you've done that, you should have found that you got the probability of 0.117. So for part C, we're going to work out the probability that x is less than or equal to 2. So that's probability equals 0, 1 or 2. So because it's a cumulative thing, so 3 different possibilities, we're going to use the binomial CD on our calculator. So you press menu 7, press the down arrow until you get to binomial CD. We want the variable, and then we're going to input our x here is going to be 2, our n is here is 20, and our probability of success here is our other parameter, 0.4. And when you put those in, you'll get the probability that x is less than or equal to 2. It gives us a probability of 0.0036. Now in this last example, we want the probability that x is greater or equal to 18. Now our calculators, it's fine to use that if you're using the tables. So in your formula book you have got tables, but it doesn't, you've got to be careful because the tables don't have all the values for n that you could be given. And to be honest, if you can use your calculator, then we'll probably stick to that. So we have your calculator always works out the probability that x is less than or equal to a number. So if we've got the probability that x is greater or equal to 18, because probabilities all add up to 1, we can say that, well, that's going to give us the same answer as finding the probability that x is less than or equal to 17. Okay, now it will be 17 because if it's equal to 18 and it's a discrete distribution, the next number down is 17. So we can input this data into our calculator. So usual thing, this time again remember it's going to be the binomial CD button. So we're going to put in our values for x is going to be 17, our n is going to be 20, and our p is going to be 0.4. And when we put that into our calculator, we have, let's see, 17, 20, 0.4. It gives us a probability of 0.9999. And leaving that in the calculator, I then pressed menu 1 minus answer, and getting my solution, which is 0.00000504. Right, following on from that, we have question 2. Ralph rolls a fair dice 8 times, or die. Suggest a suitable model for this. Now, we can say we've got a random variable x. It can be modelled on a binomial distribution. Why? Because we've got a fixed number of trials. The trials are independent, and there's a constant probability of success. So he rolls. So our n here, our n parameter is going to be 8, and suggest suitable model for random variable. A number of times it lands on a 6. So it lands on a 6. Probability it lands on a 6 is constant. It is actually 1/6. So there we go. Now, using this model, we want to calculate the following. So the first one, we want to calculate the probability that x equals 2. So we're going to have a binomial PD. So go through the usual process. We're going to have menu 7, variable, our x is going to be 2, our n in this case is going to be 8, and our probability of success will be 1/6. So we have p equals 1/6. And when we put that into a calculator, we'll get a probability of 0.260. And for the second part, the probability that x is greater or equal to 4, we've got to change that. And we're going to have 1 minus the probability that its x is less than or equal to 3. So here our x will be 3, our n is going to be 8, and our probability of success is 1/6. Into the calculator and calculate it, we get 0.0307. Now that we've just had a recap on the binomial and using the binomial to work out probabilities, we're going to move on now and look at hypothesis testing, looking at the likelihood of things happening. So I'm going to hypothesis testing. So here we are, as it says here. Let's just go through these step by step. Most important concepts in maths. Directly links real life, statistics to real life, and helps us to suggest whether there's evidence that a particular theory is true or not. For example, is a newly created drug effective in combating cancer, or whether a company produces more faulty light bulbs than it claims to. So it is a very useful thing to do and is used all the time in our daily lives. So population parameter, here are a few definitions. A population parameter is a statistical measure relating to a population. Now, you've got to remember the population in maths and in statistics is a set of items that we're interested in. And it's not just the number of people, it could be the population we're looking at, the number of the light bulbs, and so on. A hypothesis is a statement made about a population parameter. And in this part of the chapter, in this section, we're looking at hypotheses about the population parameter, P, for the binomial distribution. Okay, the other parameter for the binomial is n. So if you remember, we have the binomial, and n and p are our population. They are our parameters. So here, suppose we've got a new drug treatment which we hope will be better than a previous one. So we have to test whether this treatment is better. We could set up a trial involving a certain number of people, a sample of people. And we could then see how many people report an improvement with this new drug and then compare these results with the old one. But we all know that when you take a sample, when you get a random sample, there are, each time we take a sample, we might get different results. So we need to know whether the good results are really due to the importance of the treatment, or how random are they. If I flipped a fair coin, for example, 10 times, then you could get 10 tails, although this is extremely unlikely, but it is still possible. So just looking at this example here, we've got a trial of 20 patients with a new drug, and the condition of 15 out of these 20 patients improved quite significantly. So 15 out of 20, so 75% improved. On the average, the older drug improved the condition of 60% of the patient. So is there evidence, therefore, that this new drug is more effective than the old one? We can't just say, yes, it's clearly better because 75% of the patients have improved with the new drug compared with 60% of the old one. We need to find out the probability that 15 patients or more extreme than this, so 15, 16, 17 up to 20, improve on the old drug. If the probability is low enough, so if it's low enough that they improved on the old drug, then the situation that happened with the new drug is unlikely to happen with the old one. Then this would give us evidence to suggest that the new drug is actually more effective. So you need to think about that. Just read through that again. Read through this and make sure you understand it. Okay, so just if the probability is low enough, so the situation that happened with the new drug is unlikely to happen with the old one, then we would have sufficient evidence to suggest that the new drug is more effective. So the situation, we can model this on the binomial where P is the probability of success, so the probability that a patient improved with the new drug. So with the same example, we set up a hypothesis. Now remember, a hypothesis is a theory. So we're setting up our hypothesis that the new drug is not more effective, and we only reject this if we have a significant evidence against it. So if we're saying that our hypothesis that the new drug is not effective, that means that our probability remains at 0.6. So we call this our null hypothesis, and we have HO. So HO is our null hypothesis, and we're saying that the new drug is not more effective. So the probability of it remains the same as the old drug. So P equals 0.6. Okay, so H0 null hypothesis. And this is the hypothesis we assume to be correct. We always assume the null hypothesis is correct. So the null hypothesis uses the value of P from the data for the old drug, the original drug, so 0.6. We want to test if the new drug is better than the old one. So we also have what we call an alternative hypothesis, which we label H1. And that is that if the new drug is better, it's going to give us a better probability. Therefore, P is greater than 0.6. So this tells us the parameter if your assumption is shown to be wrong. So a test statistic is a result of an experiment or the statistic that is calculated from the sample. In our case, our test statistic is the number of people who said they had an improvement with the new drug. So our test statistic here is 15. So looking at this example, another example here that we've worked through, we've got in the past few years, a reporter has claimed that 50% of Sutton Coldfield votes for the Conservative Party. So 50% of that constituency vote for Conservative. Julie, a local resident, believes that this is not true. She believes that the probability of someone voting for the Conservative Party is less than this, and so she randomly asks 50 residents in the area. So what is our test statistic for this situation? Well, our test statistic here is the number of people that vote Conservative out of 50. what is a sensible null hypothesis? Well, we're told that our null hypothesis is we assume that what she said is true. So our null hypothesis, our HO, is that P equals 0.5. She thinks it's less than this. So our alternative hypothesis then, if she thinks it's less than this is what we're going to test, that means she thinks that the probability is less than 0.5. So we assume that the given statement is true. Here we have another example. In a report, it was stated that 65% of all current patients at Good Hope Hospital are over the age of 60. A newspaper believes that this figure is an underestimate and obtains a sample of 30 patients to verify this. First question, which you do normally get asked in an exam, is to describe what the test statistic is. So our test statistic here is the number of patients that are over the age of 60 out of a sample of 30. Now, our null hypothesis is what is the information we're given. We're assuming that 65% of current patients are over the age of 60. So our null hypothesis is that P equals 0.65. And our alternative hypothesis is, what do they say? They believe that this is an underestimate. So they think that more than 65% are. So the probability that it's greater than 0.65 is our alternative hypothesis. Different types of hypothesis testing we can do. We have what we call, what we've looked at is the one-tail test. So we have our null hypothesis where we assume what is being said is true. So in that last example, the null hypothesis was P equals 0.65. So 65% of all patients are over the age of 60, and she thought that this was an underestimate, so she thought the probability was greater, so P was greater than 0.65, and or if she thought that it was an overestimate, we could have said that the alternative hypothesis was that P was less than that. So ones where we've got an inequality is what we call a one-tail test. Now, in a two-tail test, this is where you've got to read the question carefully. Our null hypothesis was that P was equal to 0.65, but rather than saying that this was an underestimate or an overestimate, she could say that she didn't agree with this. So she's not letting on whether she thought it was an underestimate or an overestimate. So in this case, we have what we call a two-tail test, and we simply say that P is not equal to 0.65 as in the previous example. So in a two-tail test, we have to carry out a hypothesis test. We assume the null hypothesis is true and then see how likely the observed value of the test statistic was to occur. If it's less than a specified threshold, which we call our significance level, then we reject the null hypothesis. So when we carry out our calculations, if the probability is less than, say, 5%, if we're looking at the 5% level, then we reject the null hypothesis. The significance levels are usually 5% or 1%, but you will always be told this in the question. In this final example here, we're told that in the UK, 5% of students turn up late to school every day. So that is what our null hypothesis is going to be. That is what we assume to be true. So our null hypothesis, we know straight away, is going to be the probability that they're late equals 0.055%. Mr. Berwick wishes to determine at the 10% level of significance, that's our threshold, if his school has a problem with attendance. He asks the member of staff that is on duty on a random morning to monitor the number of students who are late. And he finds that 6 out of 40 students, so 6 out of a sample of 40, who passed the member of staff were actually late. So we need to write down a suitable test statistic. So here is the number of students who are late to school out of 40. So the number who are late out of the 40 is our 6. That is our test statistic. Our null hypothesis, as I've said, is 0.05, so 5%. And he wants his finding, he wants to see if he has a problem with that. So he wants to see whether the number who are late are actually greater than the study says, so greater than 0.05. So that's our alternative hypothesis. So what we're going to do is we're going to test the actual probability is more. We're going to see whether the probability is more than 0.05. So we need to count the probability that 6 or more are late. So we need the probability that x is greater or equal to 6. Now we could actually do this now. We could do this using the binomial. So we can't, if we're using the calculator, we need to write that as a probability that x is less than or equal to 5. And when we calculate this, we do actually get a probability of 0.013877. So where this is actually less than 10%, so 0.0139 is less than 0.1, so we reject the null hypothesis. You might like to pause the slide and have a go at answering this question on your own, and then I'll go through it. Right, going through this, we were told that Adam's shop opened. Since it opened, 1 in every 5 customers has bought some form of confectionery. So, with their shopping. However, Adam suspects this might have decreased in the last week. He records the shopping items of 40 customers and finds that 3 customers buy some form of confectionery with their shopping. Write down a suitable test statistic. So the test statistic here is the number of customers who buy some form of confectionery. So out of the group of 40. So here, in this question, our test statistic is 3. Write down 2 suitable hypotheses. So we're going to have our null hypothesis. Our null hypothesis is that 1 in 5 customers did actually buy, that's what we're assuming is right, did buy some form of confectionery. And he thinks that this has decreased, so that our whole alternative hypothesis is what we're testing, is that less than this, it actually decreased, so the probability is actually less than 1/5. So we're testing to see whether the actual probability is less than 1/5. So we need to calculate the probability of 3 or less. So we can actually do this now with the binomial theorem. So when I work out this probability, we have a binomial distribution, our n is 40 and our parameter probability of success is 1/5. So when I put this into the binomial CD button, I get a probability of 0.028462. So if this is less than, so if we're testing at the 1% level of significance, what we actually have here is that 0.028462 is greater than 0.01. Therefore, we accept the null hypothesis. So if it's greater than the significance level, we accept the null hypothesis. So we assume that the probability is actually 1/5 of people do buy confectionery with their shopping. On this slide here, I've put down 3 questions. There are 3 questions which you can have a go at. But don't go over to the next page. There are answers on the next slide, so you can check to see whether you understand it or not.